In our previous sections, we talked about overfitting issues. Recall that the more complex the model we choose, the more chance to lead to the problem of overfitting. When it concerns the deep neural networks, increasing the number of the hidden layers will put our model at the risk of the same overfitting. You may think then we may just reduce the number of the hidden layer there. Unfortunately, this wouldn't work because it loses the whole point of deep learning. In this section, we're going to introduce the regulation technique which we use to reduce the overheating problem of the deep neural networks. Regularization is an important and effective technology to reduce generalization errors in machine learning. It is especially useful for deep learning models that tend to be overfitted due to the diverse parameters. Therefore, researchers have proposed many effective technologies to prevent overfitting, including adding constraints to parameters such as L1 and L2 norms, expanding the training set such as adding noise and transforming data, dropout, and early stopping. Let's check out them one by one. Firstly, let's see the method of penalty parameters. This is a general method that can be also used in traditional machine learning. Many regularization methods restrict the learning capability of models by adding a penalty parameter omega of theta to the objective function j. Let's assume that the target function after regularization is j double cap. Then j double cap of theta, x and y, becomes the sum of j of theta, x and y, plus alpha omega of theta, where alpha existed in 0 to infinitive, is a hyperparameter that weights the relative contribution of the norm penalty term omega and the standard objective function j of x and theta. If alpha is set to 0, then no regularization is performed. The penalty in regularization increases with the alpha. In other words, if we found our model is too addicted to our training samples, which means overfitting happens, we can increase the hyperparameter alpha to change the situation and vice versa. As a convention in the deep learning community, we only input penalty parameters on the weight W and not consider the influence from the bias B. More specifically, we have two common forms for the penalty parameters. One of them is called the L1 regularization and can be obtained if we use L1 norm of the weight absolute value W1 as the penalty parameter omega of W as we define above. In other words, adding L1 norm constraint to model parameter leads to this equation here. Besides, if a gradient method is used to resolve the value, the parameter gradient is just like this. Similarly, we can obtain the L2 regularization by using the L2 norm of the weight absolute W2 as the penalty parameter omega of theta. In other words, adding norm penalty term L2 to prevent overfitting can lead to the cost function becomes this. Again, the gradient method can be inferred as the formula shown here, where epsilon is the learning rate. Compared with the common gradient optimization formula, this formula multiplies the parameter by a reduction factor. You may wonder what's the difference between the L1 and L2 regularizations. Here we summarize the difference between them as follows. According to the preceding analysis, L1 can generate a more sparse model, which means most of the parameters will become 0 than L2. When the value of parameter W is small, L1 regularization can directly reduce the parameter value to 0, which can be used to feature selection. From the perspective of probability, many norm constraints are equivalent to adding prior probability distribution to the parameters. In L2 regularization, the parameter value complies with the Gaussian distribution rule. In L1 regularization, the parameter value complies with the Laplace distribution rule. We have presented an illustration here to help you develop an intuitive impression on this point. The second method of regularization is called the dataset expansion, which is also a general method and can be used in traditional machine learning. The dataset expansion is the most efficient way to prevent overfitting. However, with the cost of extra training samples, usually a larger training set has a smaller overfitting probability. Dataset expansion is a time-saving method, but it varies in different fields. A common method in the object recognition field is to rotate or scale images while random noise is added to the input data in speech recognition. Besides, a common practice of natural language processing, or NLP, is replacing word with their synonyms. We'd like to point out that noise injection can add noise either to input of the hidden layer or the output layer. For example, for softmax classification, noise can be added using the label smoothing technology. If noise is added to categories 0 and 1, the corresponding probabilities are changed to epsilon over k and 1 minus bracket k minus 1 bracket closed over k epsilon, respectively. The third method of regularization is called dropout. This is a special technique that can be only used in neural networks. Dropout is a common and simple regularization method which has been widely used since 2014. Its main idea is to randomly discard some inputs during the training process. In this case, the parameters corresponding to the discarded input are not updated. As an integration method, dropout combines all the sub-network results and obtains sub-networks by randomly dropping inputs. Let's see an example figure here. On the most left, there is the original two-layered network structure. You should be very familiar with this structure by now. When we are training this network, we randomly throw away a different part of this network, as shown in the middle figure. However, in this way, we have to change the structure of the network in every training loop. It's not that convenient. An alternative way to realize this same result has been shown in the right side figure. Here, by giving the hyperparameter mu the value of 0 or 1 within a certain probability, we can use this unified form to represent all sub-network results. For most of the cases, dropout has a better performance than the penalty parameter method when training a deep neural network. However, we should also mention that this regularization method needs a great amount of data to guarantee its performance. The last method we're going to talk about is the early stopping technique, which is also an exclusive method for neural networks. This method is very straightforward. With the test on data of the validation set being inserted during the training, we can simply stop our training when the data loss of the verification set starts to increase. This means we stop early enough to avoid our model from learning too much information from the training dataset so that it increases its generalization and gets rid of the overfitting problem. And this is the end of this section.